Hi, in the last session, we talked about different 5G deployment options, and I hope you have some background and overview on 5G now. Now, let's focus on the 5G Radio Access Network or 5G RAN. Compared to the LTE air interface, the 5G air interface should meet main two requirements. First, it must efficiently utilize the new spectrum, which also lies in the millimeter wave band. Second, it needs to support the various new use cases introduced in 5G. This leads to the development of a new wireless access called NR or New Radio. In the 5G ecosystem, NR will not be the only wireless technology. Instead, it will work together with other wireless technologies such as LTE. In the new 5G designs, there are many enhancements that caters to the different goals of 5G. For enhanced mobile broadband, 5G also introduced some new concepts such as massive MIMO, beamforming, wideband carriers, and carrier aggregations, etc. Also, to support the ultra reliable low latency use cases, 5G included new features like flexible numerology, preemptive scheduling, and grant free uplink access. To improve the cost efficiency and flexibility, there are new concepts like virtualizations. So, starting from this session and in next few sessions, we will explore these defining features of the 5G radio access network and we will know that how they function. Let's start with MIMO. So the question is, how can we use the advancements in the antenna technologies to improve the capacity and the data rates in 5G? Let's begin that by exploring the evolutions of MIMO technology first. So at very beginning, omnidirectional antennas were used. They offer broad coverage, but that is uniform coverage. You can see in the top left picture, we have antenna which is providing uniform coverage in that radius. Then it was realized that the capacity of the network can be improved by using sectors, which brought the coverage like this, like at the bottom right section here. So you can see that this approach creates three different cells from a single base station. Now we can further enhance this by directional beams, more precisely to a specific user equipment or UE or some directive points. This is where beamforming comes in picture. But before learning about massive MIMO, we have to understand the basics of MIMO. In a single input and single output system, which is generally called as SISO system, we have one transmit antenna. The signal passes through a feeding channel and reaches to the single receiving antennas. Now, in this step, and according to the Shannon equation, the capacity of this system can be enhanced by either increasing the channel bandwidth or by improving the signal to noise ratio or SNR at the receiver side. Now, if you have multiple transmit antennas and a single receive antenna, then this configuration is known as multiple input, single output or MISO system. And in this setup, if the antennas are placed at least at the half of the wavelength, then each transmit antenna creates an independent fading channel to the receive antenna. This phenomena is known as transmit diversity. Now, when the same data sent through these multiple channels, then they are affected by their independent channels. And by combining these received signals at the receiver, the signal to noise ratio or SNR gets improved, and that enhances the channel capacity. This approach is especially beneficial for downlink because the multiple antenna setup requires more space, so they can easily locate it at the base stations. In a similar fashion, if there is a single transmit antenna and multiple receive antennas, then we also achieve independent feeding channels. This is called receive diversity, and it also enhances the received signal to noise ratio or SNR by combining the effects of different feeding channels. In this setup, the signal processing occurs at the receiving end. Now, when the multiple antennas are used at the both end, means at the transmitting end and at the receiving end, then this is referred as MIMO or multiple input, multiple output setup. And when there are at least 16 transmit antennas and 16 receiving antennas, then it is often called as massive MIMO. However, some says that the minimum number of antennas for massive MIMO should be 32 antennas or more for each side. Now MIMO offers three main methods to enhances the data transfer rate. First, when signal to noise ratio is low, then the diversity techniques can be applied to improve the signal to noise ratio, just like before. However, if signal to noise ratio is high, then spatial multiplexing can be used to increase the data rates and system throughput. In spatial multiplexing technique, throughput is improved by transmitting multiple data streams simultaneously over the channel. Now there are two variants of spatial multiplexing. First is open loop spatial multiplexing and second is closed loop spatial multiplexing. In open loop spatial multiplexing, the transmitter does not require channel state information. However, it is less efficient than the closed loop spatial multiplexing. In the closed loop spatial multiplexing, the transmitter receives the channel state informations through the feedback from the receiver. And with the knowledge of the transmitter, appropriate precoding is done in the transmitter and processing is done in the receiver side. This allows the data streams to be separated effectively. The maximum number of streams in such MIMO systems is limited by the minimum number of either transmit antennas or receiving antennas. Now, if all the receive antennas belongs to the same UE, it's known as single user MIMO, like you see in the top section of this picture, where all the receiving antennas belongs to the same UE. So it is called single user MIMO. Same way, if multiple streams belongs to the multiple UE at receiving end, and these simultaneous streams received by different UEs at the same time, then this setup is called multi-user MIMO, like you see in the bottom section of this picture. Now, this is the third MIMO technique, where the same signal is transmitted from each transmitting antenna. But these signals are phase shifted, and the phase adjustment is done in such a way that the signal power is maximized to some specific point where the UE is receiving the data. So this process is known as beamforming, which can be implemented in three different ways. The first method is analog beamforming. In analog beamforming, the phase of individual antenna signals are adjusted in the radio frequency domain. This adjustment influences the radiation pattern and the gain of the antenna array to provide the enhanced coverage. In digital beamforming, which is also called as baseband beamforming or precoding, this signal is precoded during the baseband processing before the RF transmissions. Means the processing occurs in the frequency domain. As a result, different signals are transmitted from each antenna. These are represented by different colors in this picture here. And the third is hybrid beamforming, when both analog beamforming and digital beamformings are combined. This technique is referred as hybrid beamforming. Beamforming enables the concentration of power towards a specific spatial region or a specific UE. So you see in this picture here. As a result, now the scheduler has an additional responsibility because now it has to plan not only the time domain and frequency domain, but also the spatial domain. So this is how the beamforming works in 5G. LTE and its evolutions supports different forms of MIMO, like transmit diversity, spatial multiplexing, multi-user MIMO, etc. But in 5G NR, since there are spectrums in the millimeter wave bands, and as a result, the antenna size reduces significantly with such increasing frequencies. So it is easy to place many number of antennas in some form of array and place them together in one small package. So this huge array of antennas transmits narrow beams. And when the power from the different antennas combine in one direction, it acts like a strong beam. So this is the concept of beamforming. So in beamforming, the phase of the transmitting signals is adjusted in such a way that it adds a power in some specific direction to form a beam and eliminates each other power in the other directions. So that was one thing. But we also consider that millimeter waves have poor propagation characteristics. So for millimeter frequency bands, beamforming is important to serve 5G users. So here is a quick summary on what are the key benefits of using massive MIMO in 5G RAN. Number one, massive MIMO systems have a larger number of active antennas elements. Number two, massive MIMO allows for more focused energy to improve signal strength. Number three, high intensity beam signals are less impacted by interference, so it has better signal quality. Number four, in good SNR conditions, more special multiplexing layers are possible, so you can enhance the data transmissions. Number five, massive MIMO improves the cellular network throughput and coverage. Number six, massive MIMO can serve more users simultaneously. Number seven, massive MIMO supports two-dimensional beamforming, so it offers better signal precisions in both horizontal and vertical planes. Okay, so that's it for today. In the next session, we will be talking about 5G spectrum. So stay tuned for the updates. If you did not subscribe till now, then please subscribe to learn and grow community for regular updates. If this video is informative, then please like this video, comment on video, and don't forget to share. Thank you for watching.